I have this CNC lathe here, and I'm making some improvements to it over the last few weeks. And one of the improvements I've been doing is changing out the encoders to be linear scales on it for better motion control. So instead of on the servos, it tracking position through the rotary encoders, it's going to use these linear glass scales here. So it directly tracks the position of where the cross slide is instead of how many revolutions the motor has turned. So it tracks it directly, no slip in the belt, no backlash, no other issues. I also did this to hopefully have a good control over thermal growth that might occur on it. These glass scales do have lower thermal growth than the steel does, so it should be a better reference length. What I want to focus on most in this video is the electronic side of how I connected and interfaced it with the controller. So most CNC lathes for the encoders need some form of quadrature to track its position. So two phases out of sync 90 degrees, phase A, phase B. And rotary encoders do the same thing, linear encoders also, 5 volts peak to peak. So the signal should be pretty close to being compatible, drop-in replaceable. I did have to do a few tweaks to make it understand the signal. So the controller I'm going into on it is a Fagor 2025 controller. No, it's a Fagor 8025 controller. Here on the inside of the controller cabinet, it has the various inputs for the encoders. A1 through A5 here are for the various inputs for the different axes. And A1 is X, A3 is Z, and it has some little dip switches beneath each input, and those dip switches say what type of signal it takes. This one in here is still set to differential square wave, while this one in here is single-ended square wave, as denoted by this little label here. So it is not a reverse square wave as TTL, as actually RSS 422, that's the format for the differential square wave. TTL is known as the simpler one, which is single-sided. That is what you find on many of the more inexpensive encoders. That is what I have it configured to use. So it only uses A, B, and Z. During testing, I'm using this RSS 232 breakout board and this DB15 breakout board in here to translate over the wire combinations needed. So right in here I have just the signals coming from the encoder right in here that leads back there. So I have on the first pin, I think it is 5 volts, then 0 volts, then A, then B, then Z. But unfortunately on this one, it did not come with the Z signal. That marker pulls every 50 millimeters. It has a spike telling you where you are. So that marker pulse was actually needed for some functions on the controller. So right now I'm just tricking it by giving it 5 volts. I have a jumper between 5 volts and Z, marker pulse. And that little wire in there enables it to do the home search. So I'm fooling it right now because my encoder does not support that. I'm examining it on the oscilloscope to see if the signal is what I expected. So right under the headstock is this small gap And in there I was able to fit this 3/4 square bar of stainless steel, and it slips underneath onto the bed. So it mates right there on the 60-degree dovetails that are on the beds of these hardened chucker lathes. And it wraps around, goes to the other side, and holds up one end of the linear scale. The little cutout on there, as you see, is to get access to a screw head. That little mounting screw there is used to hold on the way covers. So here I'll show more of a close-up showing how the reed head is mounted. So here I have a 1/2 inch thick plate of 304 stainless steel. I cut a little shoulder in, and it sets the proper height for the encoder head. Right here there's a pretty big gap, enough that I can put a protective cover in to lay over the scale and protect it from any chips that might fly onto it or coolant. It is in a little vulnerable of a position right now. Here I'm testing the Z, going back and forth, bouncing. And here on the scope you can see the signal. So there I have it triggering each time the servo crosses 0 volts. In the background you see the quadrature signal, and the purple line right there is the analog voltage being given to the servo drives. I have the deceleration time right now set at about 5 milliseconds, or I have it set at 45 millisecond deceleration time right now. That really helps prevent as jerky of movements. But in here, when I zoom in on it, you can start to see the signal. So there it is, 2 phases. Yellow there A, blue is B, 90 degrees out of phase from each other. That's how quadrature works. So here on the controller, I'll start to show some about how it was configured. It turned out to be not that difficult once I really discovered how. Using the OEM technical manual, it gave me a lot of good advice on the parameters needed. So now 300 series are where the Z axis starts. Type in 300, hit recall, and down in here you can start to see the resolution is set to 1 for the scale's feedback. I also needed to change the other parameters in here to say that the feedback is in millimeters rather than inches. Right now I have the display set to inches, but almost any DRO or linear encoder you get is going to be in millimeters. So the feedback system is in millimeters, while all the rest of the machine is set to be in inches right now. One of the more difficult things to problem solve during the integration of the linear scales was making the home search work. That was not working because I learned through reading more detailed into the manual that it expects a marker pulse after the limit switch is hit. So over here it has inductive limit switch. So touching on it here does nothing, but once it comes in contact with a metallic object in here, you see it lights up. So that is the home switch. That little metal strip in there, once it hovers over the inductive probe there, it tells it that's at home. But once it reaches there, it does other things too. Then it activates a second feed rate, and it keeps traveling at a slower speed until it reaches the marker pulse. But sadly, my scales did not have that option when I bought them a few years ago. So I had to trick it. So I gave it a 5-volt always on signal and told it to expect a positive pulse for the marker, and that basically fooled it. So it's always getting the marker pulse 5 volts high, and that's how I fooled it into homing without having that built into the scales. So now, once I home it, it works. So to home on this version of the controller, what I do is I go into select the axis, Z, home, then you go cycle start, and now you can see that it's about a home. There, it hit the red, little LED, and it's at home right now. Hit the limit switch, then it got the fake marker signal, and now Z is 0 down. So that's the overview of how I got it put on here. I'm going to route the cable much better now that I know that it can electrically work. I'm also going to build a protective cover for the scale so that the chips and coolant don't get onto it. The x-axis is going to be the topic of another video. It's going to be much harder to put on here because it'll need to fit over some weight covers that are right here under the headstock. I definitely hope to get some 1/10 of a micron scales on here so that when I do put this into a resolution of 10 millionths of an inch, I have much more confidence that it'll repeat to that position. I know that it's not rated for those accuracies, but I'll get very good repeatability to hit a value over and over again.